What if you could teach an AI to be the ultimate stress tester? To creatively and just relentlessly find the breaking points in other complex systems, like the very robots we're about to share our homes and workplaces with. Okay, let's get into this fascinating new research where scientists did exactly that. So, we're right on the edge of that future we always hear about, the one where humans and robots are working side by side on everything from building cars to assisting in surgery. The vision is this seamless, super efficient collaboration. But, and this is a big but, that brings us to a massive problem.
So what could possibly go wrong? Well, in a task as simple as this one, a human labeling packages, while a robot stamps them. Just think about it. The robot's next move depends on where the objects are, which one the human grabs, how the human moves their arm. The number of possible interactions is, for all practical purposes, infinite. So how in the world can we ever be sure the robot will always be safe?
Now, the old way of tackling this is an approach called quality diversity. The goal here isn't just to find the one single worst-case scenario. No, the idea is to generate a whole library of diverse and challenging situations to get a really complete picture of a robot's blind spots and weaknesses.
And that sounds great, right? A really thorough approach. But here's the catch. In practice, the old way of testing hits a massive wall. It creates a huge bottleneck because it's just painfully slow. And the reason it's so slow? Well, it's basically a brute force method. The system has to run millions, literally millions of complete, one-by-one simulations of every scenario it dreams up. I mean, if each simulation takes just a few seconds or maybe even minutes, well, you do the math. That balloons into weeks or even months of pure computation time. And this image, this shows you exactly what you get for all that work. This is a heat map. The colored spots are the failures the system managed to find. But I want you to look at all that white space, all of it. Those are giant, gaping blind spots, untested areas where some really dangerous failures could be hiding, completely undiscovered. Yeah, the scale is just staggering. We're talking about needing to run over 1 million individual, time-consuming evaluations just to get that patchy, incomplete picture we just saw. This right here, this is the bottleneck that has been holding back the development of safer robots.
But okay, what if you could cheat? What if you didn't have to run every single simulation? This is the breakthrough from the research paper. This is a much, much smarter way to test.
Here's the key insight, and it's brilliant. The researchers decided to use a deep neural network as a kind of AI crystal ball. Instead of running a full, slow simulation, this AI, they call it a surrogate model, learns to predict the outcome. It can guess whether a scenario is likely to cause a failure, and it can do it almost instantly. So how does this AI crystal ball fit into their new method, which they call DSAS? It's a really clever 4-step feedback loop. First, the AI crystal ball predicts the outcomes for thousands of different setups. Because it's so fast, it can then explore millions of potential failure scenarios in just seconds. Then, and this is the genius part, it only sends the most interesting and challenging predictions to be run for real in the full simulation. Finally, the results from those real simulations are fed back to the AI, making its crystal ball even more accurate for the next round. It's a system that gets smarter as it works.
Okay, so the theory sounds great, but does this whole AI crystal ball thing actually work better? Well, let's take a look at the results because they are pretty dramatic.
All right, check this out. It's a perfect before and after. On the left, you recognize that gappy heat map from the old method. Remember all those blind spots? But on the right, that's the result from the new AI-assisted method. Just look at how it has found this vastly richer, more complete map of potential failures. It's effectively filling in all those dangerous blind spots. I mean, it is a night and day difference.
And the numbers absolutely back this up. This table shows the QD score, which is basically a measure of how well a method finds a wide variety of failures. A higher score is better. The old way, that algorithm called Map Elites, scored just under 12,000. But the new DSAS method, it scored over 21,000. That's nearly twice as effective at finding a diverse set of problems.
And here's the real kicker. For more complex robot tasks, where a single simulation might take a couple of minutes, this new method isn't just more thorough, it's also significantly faster in terms of actual real-world time. So it's both better and faster. A total win-win.
This is all great in a computer simulation, but does it find failures that actually happen in the real world? Well, the researchers tested that too, and the answer is a definitive yes.
So here's a failure the AI found. The human finishes with an object, and the robot gets confused about where the human will go next.
It makes the wrong guess and starts moving towards an object on the far side of the table. By the time it realizes its mistake, it has to take this long, inefficient path all the way back, causing a huge delay. In this next failure, the AI discovered that a specific arrangement of objects forces the robot's arm into this strange, contorted path. As it moves, it gets so tangled up that it nearly collides with its own body, forcing it to stop and completely replan its motion. This is a subtle but critical failure mode discovered entirely by the AI stress tester.
So, what does all this mean for the future? This goes way beyond just one experiment in a lab. Let's look at why this matters so much.
The crucial takeaway is this. We now have a tool that acts as a powerful accelerator. It's a way to find bugs in dangerous edge cases in simulation, which helps us avoid costly failures and, most importantly, takes a massive step toward making the robots of the future safer for all of us before they ever enter our world.
And this is the goal, stated perfectly by the researchers themselves. They see this as a valuable tool to make the entire process of developing and testing these complex systems faster and safer, right before they're deployed for real.
Which leaves us with a final fascinating question. If we can teach an AI to be this good at finding the hidden flaws in a robot's programming, what's next? What other complex systems, from self-driving cars to financial networks, could we make safer by unleashing an AI to find their blind spots?